Okay. So you have to click on got it. Okay, so today's speaker is Amnon Neeman, and the title of his talk, you can see there, is Finite Approximations as a Tool for Studying Triangulated Categories. Please, Amnon, go ahead.
So, first of all, let me apologize for those who have heard early versions of this talk. I'll try to go over the early parts quickly. So, the idea of putting a metric on a category goes back to a very old article by Lawvere. And all it amounts to is you assign a positive real length to every morphism with the properties that all identities have length 0 and the triangle inequality holds. And by the triangle inequality, I mean that the length of the composite is less than or equal to the sum of the lengths. Now, so the literature goes back to the 70s and early 80s. And one of the basic things you can do is once you have a category with a metric, you can define what you mean by continuous functor. Okay, once you have two categories, both of which have metrics, it makes sense to ask for a functor to be continuous. And it also makes sense to ask for a functor to be uniformly continuous. And I will leave the epsilon delta definition to you. You'd like to view two metrics on one category is equivalent if the identity is uniformly continuous in both directions. And again, there's an epsilon delta definition, which I skip. The next idea is a Cauchy sequence. And again, this copies what you do in analysis, except that morphisms have directions. And for a Cauchy sequence, they all have to point the same way. So for us, they all point in the increasing direction. And you define a sequence to be Cauchy if the lengths eventually get to be arbitrarily small. And now the next notion is completing a category with respect to a metric. And what I do is slightly non-classical, so I'm going to add the unnecessary assumption that the category is Z-linear, which means that Hom AB is an abelian group for every pair of objects. And the composition is bilinear. Okay, so the point is that every category admits a Yoneda embedding into a category of functors, and the category of functors is closed under colimits. And the simple-minded idea, which is all we'll use in this lecture, is that the completion of the category C with respect to the metric is just the collection of all colimits in mod C of Cauchy sequences in C. And the important thing that's new is that we don't want to consider the entire completion, we want to consider a subcategory of it. And S of C is defined by the rule, a functor belongs to S of C if it takes sufficiently short morphisms to isomorphisms. If there exists an epsilon, which depends on F, such that morphisms of length less than epsilon go to isomorphisms. Okay, so this defines first S of C, and the only thing I can observe in this generality is that equivalent metrics lead to identical Cauchy sequences, identical completions, and identical S of C. So all of these constructions depend only on the equivalence class of the metrics. Okay, so you've been very patient with me, and I ask for your patience for a little longer. I want to specialize. I don't want to look at all metrics on all categories. I want to look at triangulated categories with metrics. And the reason is that in triangulated categories, there's a good notion of translating a morphism. And we only want to consider translation invariant metrics. So the point is that in a triangulated category, there are homotopy Cartesian squares. And we view two parallel morphisms in a homotopy Cartesian square as being translates of each other. And we insist that the translate of the morphism F should have equal length. So the length of two parallel morphisms in a homotopy Cartesian square are equal. Now, every morphism can be translated to start at the origin. And if the metric is translation invariant, the length of F has to be equal to the length of G. And therefore, the metric is completely described by the length of morphisms starting at the origin. So I can, okay, and I will soon assume that all my metrics are non-Archimedean. And up to replacing a metric by an equivalent, I can assume that the values of the metric are all powers of 2. So I allow 0 and infinity to be powers of 2, 2 to the minus infinity and 2 to the plus infinity. And to know everything about the metric, it suffices to specify the balls of radius 2 to the n, or 2 to the minus n. And then if I know the balls, I can tell you the length of any morphism. There is a formula which I skip. Okay.
So sorry, so you admit infinite distances. So it's a generalized.
Make infinite distances. Up to equivalence, yes. Okay. So now let S be a triangulated category. And now I'm going to define a good metric. So it's a translation invariant metric. It's specified by balls centered at the origin. And the balls have to contain the origin, and they satisfy, you want the strong triangle inequality to hold. So you want the metric to be non-Archimedean, and I remind you, this means that the length of the composite is less than or equal to the maximum of the lengths. And in terms of balls, this translates to a convexity on the balls. If X is an extension of B and B dashed, and B and B dashed both lie in the ball of radius 2 to the minus n, then so does X. So this is the non-Archimedean hypothesis. And of course, you want the ball of radius 2 to the minus n minus 1 to be contained in the ball of radius n. That's obvious. The balls should decrease as the radius decreases, but I want them to decrease rapidly. So I want the ball of radius 2 to the minus n to also contain the right and left translates of the ball of radius 2 to the minus n minus 1. And if you want an example, anytime you have a T structure, you can declare that Bn is equal to S less than or equal to minus n. We'll come back to this example. Well, you've been very patient with me, and now it's time for a theorem. I've given you a whole bunch of definitions. Now the theorem says let S, well, okay, let's start in general. Let S be any category with a metric. We define the completion of the category with respect to the metric. And inside the completion, there was a certain subcategory we called S of S. Now, if S is triangulated, then you can declare that the distinguished triangles in S of S are the colimits in S of S of Cauchy sequences of distinguished triangles in S. So if you have a Cauchy sequence of distinguished triangles, and if all three terms in the colimits lie in S of S, then you declare that the colimit is a distinguished triangle. And now, if the metric is good, then it turns out that with this definition, S of S is triangular. So now, this is a theorem, and I should point out that it's a surprising theorem, because we've all been taught that triangulated categories don't reproduce. So the old wisdom is that in order to produce new triangulated categories out of old ones, you have to have some enhancement. And here I gave you a recipe, which didn't take me too long, and started with a triangulated category, okay, with a metric, and out of it produced another. Of course, examples are in order, because if I always get 0, you will not be impressed. Or if I always get S, you will not be impressed. So let's look at this example. Let R be an associative ring. Let's assume that R is an Ethereum. Then dB of R proj has for objects the bounded complex of finitely generated projective R modules, and dB of R mod has for objects the bounded complexes of finitely generated R modules. So dB of R mod is bigger than dB of R proj. And okay, there's an algebraic geometry version, which I will leave out for now. And the theorem says that the S construction takes the little category, so with an appropriate choice of metric, the S construction takes bounded complexes of projective modules to bounded complexes of all finitely generated R modules, and vice versa. There's a metric on the opposite category of dBr mod, such that when you apply S, you get dB of R proj up. And there's also an algebraic geometry version, so a scheme version, a global version. And it tells you that the S construction goes back and forth between the perfect complexes and the bounded derived category of coherent sheaves. And now we really should stop and think a little, because at least the birational geometers out there have been studying the minimal model program using derived categories for a while. And the philosophy is that a flip should reduce the derived category, and a flop should leave it unchanged, okay, at least up to finitely many choices. So flops don't change the derived category, and flips reduce it. And somehow the minimal model program should be to try to reduce the derived category as much as possible. And algebraic geometers or birational geometers have been known to argue about which is the better invariant. And what I'm telling you is that this particular argument is a waste of time. These two categories know each other. They're interchangeable. Each of them contains the information of the other. Okay, so I've given you one theorem, but I tell you that this is just one of a whole string, and it's really part of a general theory. And what really we should be looking at is a much more general result. All of these, everything I've said is really a special case of the fact that certain categories are approximable or weakly approximable. So next comes a technical definition. I have to tell you what it means, and the technical definition is forbidding. It's technical. So it's best to actually think of an analog. So approximability is about trying to do pretend Fourier series on triangulated categories. So you think of the triangulated category T as some sort of analog of the space of, let's say, Lebesgue measurable functions from the circle to the complex numbers. And what do you do in ordinary Fourier analysis? You choose a particularly good function, the exponential function, and you then form the vector space of low-degree trigonometric Laurent polynomials. and try to show that any function f has a good approximation by low-degree Laurent trigonometric polynomials. And by a good approximation, you mean you have to measure the difference, so you introduce a Banach norm, let's say the LP norm, to measure the difference. So we want a triangulated category analog. So in the triangulated category T, the exponential function will be replaced by a compact generator. The vector space of low-degree Laurent trigonometric polynomials will be this strange symbol. And the Banach norm will be replaced by a T structure. And now the definition involves all of these. So compact generators occur, T structures occur, and those strange things, the replacement for the low-degree Laurent trigonometric polynomials occur. So I should quickly remind you what these things mean. So an object in a triangulated category is called compact if hom G blank commutes with coproducts. And a compact object generates if every non-zero object admits a non-zero map from some shift of G. So this is a compact generator. Now, a T structure. So an example of a T structure is to take the derived category of all complexes of R modules, and you declare that the negative part are all the complexes with vanishing positive cohomology, and the positive part are the complexes with all vanishing, all those complexes with vanishing negative cohomology. Anyway, the general definition of a T structure is that on the category T, you give a pair of full subcategories, the positive and the negative. And the important property for us is that if you take the negative objects and shift them, then you stay inside the negative objects. And why is this important for us? You see, the T structures are supposed to play the role of a norm on our category. And we already know what a translation invariant metric on a triangulated category is. And norms are, among other things, translation invariant metrics. But what's special about a norm, among all translation invariant metrics, is that the ball of radius 1 around the origin governs everything. Every other ball is a dilation of the ball of radius 1. If I tell you the ball of radius 1, then I've told you all the balls of any radius. And here I want to declare T less than or equal to 0 to be the ball of radius 1. And the ball of radius 2 to the minus n is going to be the nth translate of the ball of radius 1. And the inclusion here, the highlighted inclusion, says that the ball of radius 1/2 is contained in the ball of radius 1, which is really all you need. Okay, but you do want it to be a good metric, and that means that the ball of radius 1 has to be convex, and the rest of the axioms guarantee this. So you can get a good metric by setting the ball of radius 2 to the minus n to be the nth translate of the ball of radius 1. And normally this is denoted by T less than or equal to minus n. Okay, so this has done T structures and compact generators for us, and now we come to the analog of the low-degree trigonometric polynomials. So suppose I give you a compact generator G, and an integer, then I somehow want to form the analog of the trigonometric Laurent polynomials of degree less than or equal to a. And if we're going to talk philosophy, in the way you form low-degree trigonometric polynomials is you take the exponential function, you take powers of it in the range between minus a and a, and then you take linear combinations. And now we want to do the same with a compact generator G. So how do you produce new objects out of G? You can shift, you can take direct sums, you can take direct summands, and you can take extensions. And the idea of all of these constructions that I will show you is that you place some limits on what you allow. So the first is this, which is due to Bondel and Vandenberg in a 2003 paper. And the only limit is on the number of extensions you can use. In another 2003 paper by Alonso, Jeremias, and Souto, they define this object, and the bound is on the shifts allowed. You only allow the shifts to be up to degree A. And of course, you can combine it and make the bound on the shifts stronger. You only shift between degree minus A and A. And finally, you can combine the two and form the smallest of all of these. And this is where you only allow yourself to shift in the range minus A to A, and you only allow yourself to form up to A extensions. So now I've defined all the terms, and the definition, I mean, you can read the definition, you know what all the terms mean, but you still have to know what the definition means in the real world. And the highlighted part is best illustrated by a picture. It says that if you take an object F, which lies in the ball of radius 1 around the origin, then there is a low-degree trigonometric polynomial, an object E, which doesn't take much effort to build out of G, and an arrow from E to F of length less than or equal to half. And the highlighted part here says that there are no homomorphisms from G into either T less than or equal to minus A or T greater than or equal to A. And this turns out to be a very strong hypothesis. It essentially forces the metric to be unique up to equivalence. So I have no justification for it from the perspective of trying to do the analysis analog. It looks strange. But what can I say? It turns out that this theory has many examples. So now we come to theorems, and the first theorem is that there are lots of examples. Many triangulated categories are either weakly approximable or approximable. So there's a list of theorems here, and the ones that will play the biggest role in this talk are the two highlighted ones. So for any scheme X, the relative derived category is weakly approximable basically always. And if X is a quasi-compact separated scheme, then the absolute derived category, unbounded derived category of quasi-coherent sheaves is approximable. So here are references for the proofs of these statements. And now, okay, So I've given you a strange definition, the definition of approximable triangulated categories. I told you that there are lots of examples, but now I have to find a real application. I have to find a theorem that people actually care about. So in order to give you this theorem, I remind you of an old definition. Let S be a triangulated category and G an object. Then G is a strong generator if there exists an integer L such that G generates S using no more than L extensions. So this definition goes back to Bondal and Vandenberg in 2003. And the category S is strongly generated or regular if there exists a strong generator G in S. So those are definitions. And now the theorems say, okay, let X be an Euclidean scheme. It says that the perfect complexes are strongly generated if and only if X is regular and finite dimensional. And the boundary derived category of coherent sheaves is basically always strongly generated. It's strongly generated under very mild hypotheses. So both of these theorems appeared. Well, in both cases, the papers, well, okay, so I could go into more detail, but the theorems in this generality go back to 2021. And I really don't want to say any more about them. So if I were honest, the honorable thing to do would be to spend the rest of the talk on this, tell you what was known before, why people cared about it, who proved what and when, what the open questions are. But as I said, if I did this, it would take the rest of the talk. And I want to talk about my preprints. I want to persuade you to read my more recent papers. So let me do none of the above. All I want to say about this particular theorem is that an enormous amount was known in equal characteristic. And what stands out about these two 2021 results is that they work in mixed characteristic. Okay, let's move on. So you can find many surveys of the work I'm about to describe, but most of the actual papers are in preprint forms, especially those. And now we move on to other topics. So the first thing I want to define is what it means for two T structures to be equivalent. So let T be any triangulated category, and suppose I give you two T structures on it. So I declare them equivalent if the metrics are equivalent. And remember, a T structure is a norm, which means that the ball of radius 1 governs everything. So to say that two norms are equivalent is to say that the ball of radius 1 with respect to norm 2 contains some small ball with respect to norm 1 and is contained in some large ball. And in T structure terms, this says that T2 less than or equal to 0 contains T1 less than or equal to minus A and is contained in T1 greater than or equal to A. Okay, and now we come to an old theorem of Alonso, Jeremias, and Souto, which tells us that if T is a triangulated category with coproducts, then, and G is any compact object, then there's a unique T structure generated by G. By this I mean that in my black box constructions, there was this category that you get by taking the object G, shifting it taking all positive shifts of it, and closing under coproducts, direct summands, direct sums, and extensions. And you declare this to be Tg less than or equal to 0, and it turns out that it is a Tg less than or equal to 0 for T structure. And the Tg greater than or equal to 0 is what it has to be. There's a formula. And then one proves relatively easily that if G and H are two compact generators, then the T structures they generate are equivalent in the sense of equivalence I gave above. So in other words, and what this means is that if the category has a compact generator, then it also has a preferred equivalence class of T structure. You declare that a T structure is in the preferred equivalence class if it's equivalent to a T structure generated by some compact generator, and therefore by every compact generator. Now, given any T structure, it's customary to define the negative objects, which is the union of the T less than or equal to n, the positive objects, which is the union of the T greater than or equal to minus n, and the bounded part of the T structure, which is T minus intersect T plus. And this all depends only on the equivalence class of the T structure. And therefore, if you have a compact generator, a single compact generator, then you have a preferred equivalence class of T structures, and therefore you have a preferred corresponding T minus, T plus, and TB. And these don't depend on any choice. They're intrinsic. And now we go on to the next intrinsic thing. If we have a compact generator G, then there is somehow a preferred equivalence class of metrics. And so up to equivalence, we can speak of the metric on the category. And with respect to this metric, you can look at the closure of the compact objects. So you declare this to be Tc minus. And the definition is that every object in Tc minus admits arbitrarily good approximations by compacts. And concretely, this means that for every epsilon greater than 0, there exists a morphism of length less than epsilon from a compact object to F. Remember, morphisms have directions, so you have to choose on which side you approximate. Anyway, this is the definition of the closure of the compacts. And we define TBC to be the intersection of the bounded and the closure of the compacts. And the closure of the compacts is intrinsic, and so are the bounded, so therefore so is the intersection. And we're only assuming so far that the category has co-products in a single compact generator. But if so under these assumptions, T minus, TB, and T plus are thick triangulated subcategories, so they're closed under triangles and under direct summands. And if T is weakly approximable, then the closure of the compacts and the bounded parts of it are also thick triangulated subcategories. So I've defined all of this intrinsic structure in gorgeous generality. And then there are the theorems that tell you that the unbounded derived category of all complexes of R modules is an approximable triangulated category. So all of this theory applies. You can define all of these intrinsic subcategories, and you can compute what they are. And when you compute, you discover that you meet old friends. So here's the computation in front of you. And you can also do it for the unbounded derived category of quasi-coherent sheaves on the scheme. Okay, so I assume that the ring R was left coherent. I assume the ring R is left Noetherian, or that the scheme is Noetherian. But if you're careful, then the computations make sense for any ring and any scheme. You just have to carefully think about what you mean by the bounded derived categories of whatever. So those need to be defined with more caution. But they're classical categories that appear way back in Illuzy's 1971 exposés in SGA6. Okay, so far I've told you that an approximable triangulated category has all of these intrinsically defined subcategories, and that in special cases they compute to be things that you have known and loved for decades. But we are still waiting for a theorem, a real theorem that will convince us that something genuine and interesting is happening. And for the next theorem, it helps to remember functional analysis. So take the space S of all the big measurable real-valued functions on the real line. Then you can consider the bilinear form taking a pair of functions to the integral of the product. Of course, this integral doesn't have to converge. So it's a pairing which takes two functions to either a real number or undefined. So far, it's clear that we are being too general. But as you learned in functional analysis, if you restrict, so if you assume that F is LP in LP and G is in LQ, with P and Q satisfying the usual identity, then the pairing takes F and G to a real number. The integral converges, and you have a map from LP to the dual of LQ, and from LQ to the dual of LP. And one of the first theorems we learn in real analysis is that these are isometries. LP is the dual of LQ, and LQ is the dual of LP. Now, there are category theoretical versions. So given an R-linear category, there is an obvious pairing taking a pair of objects A and B to Hom AB. So this is a pairing from T up. Unlike the integral, it's not a symmetric pairing. You have to keep Hom AB is not symmetric in A and B. So you have to keep track of which variable comes first. So it's a pairing from T up cross T to R modules. And it induces two Yoneda maps. There's a map from T to the dual of T up, and a map from T up to the dual of T. And in general, these maps don't tell you all that much. But just like in the real analysis example, in the functional analysis example, you might get much more information if you restrict to well-chosen subcategories, to LP and LQ. And if T is an approximable triangulated category, then it comes with a whole lot of intrinsically defined subcategories. And you can pair any two of them you wish. So I have given a name to two of the pairings. And now what I really want you to notice is the generality of the theorem on the next page. It tells you that in this gorgeous generality, in the world of approximable triangulated categories, where with some finiteness hypothesis on the Hom sets, so for a compact generator G, you want the Hom sets to be finite R modules. Then, well, let's just look at the thing that's highlighted in red. Then the composites from far left to far right are fully faithful, and you know the essential images. So they're fully faithful embeddings of the left-hand side in the finite homological functors on the right-hand side. And a homological functor is finite if for every object C, Hn of C is finite for every integer n and vanishes for all but finitely many n. Okay, and the interesting thing is that if X is a scheme proper of an Euclidean ring R, then T satisfies the hypothesis of the theorem, and in particular, the bounded-derived category of coherent sheaves embeds fully faithfully into the finite homological functors, onto the finite homological functors on the perfect complexes. Okay, big deal. So how can we use it? So now let's see an application. So suppose X is a scheme proper of an Euclidean ring R. For example, the complex numbers. So then it's classical that you can look at coherent algebraic sheaves on X or coherent analytic sheaves on X. And there's a functor which takes coherent algebraic sheaves to coherent analytic sheaves. And on the level of derived categories, it takes bounded complexes of coherent sheaves, coherent algebraic sheaves, to bounded complexes of coherent analytic sheaves. And one way to state Sayers-Gaga theorem is that the functor L is an equivalence of categories. And for those of you who are not familiar with the other examples, this is only one of a whole string of Gaga theorems. So there is, for example, if R is a complete local ring, then you can look at the bounded derived category of coherent sheaves on X. And for the analytic category, you can look at the coherent formal sheaves on the formal scheme X analytic. And there's a Gaga theorem there too. It's called Géométrie algébrique et géométrie formelle, and it's due to Grothendieck. And there's a Berkovich space version. There's a whole lot of Gaga theorems. And now I will show you how to prove them all in a unified way. They're really all one theorem, and I'm going to give you the proof. And it's going to be an application of the representability theorem. So how are we going to prove this? So let A be an algebraic perfect complex, and let B be a bounded complex of coherent analytic sheaves. Then there's a pairing which takes them to Hom AB. Well, okay, they don't belong in the same category. One is algebraic and one is analytic. So we have to take Hom from L of A to B in the analytic category. So this gives us a map from coherent analytic sheaves to the dual of the perfect complex, of the perfect algebraic complexes. But it's a theorem in complex analysis, and even an easy theorem, that this is a finite homological functor. But the finite homological functors are exactly the image of the functor y composed with I. The functor y composed with I is fully faithful, and the essential image are the finite homological functors. So therefore, there's a functor R which makes this triangle commute up to a canonical isomorphism. So, in other words, there's out of thin air, we have produced a functor which takes a coherent analytic sheaf and produces out of it something algebraic. It's a piece of black magic. Anyway, so this black magic bought you a functor R, which goes in the wrong direction. And it's easy to see that it's right adjoint to the functor L. And to prove the Gaga theorem, it suffices to show that the unit and co-unit of the junctions are isomorphisms. And proving that the unit and co-unit of the junctions, proving that certain morphisms are isomorphisms can be done against test objects. So you need to choose a collection of objects which is well suited for this particular check. And it turns out that the perfect complexes supported at closed points do the job just beautifully. And in fact, the rest of the proof is very easy. So I leave out the details, but I should give credit where credit is due. So the central idea behind this beautiful proof of Gaga is due to Jack Hall. So Jack Hall had the idea that it was possible to prove all the Gaga theorems in a unified way using representability theorems and by the simple trick. Of course, at the time Jack Hall came up with the idea, the representability theorems weren't strong enough. So my contribution was that I proved the representability theorem that made the passage from the central idea to a complete proof of Gaga trivial. So, I mean, after all, Jack Hall's idea was brilliant enough that somehow I felt that it was wrong to mire it in technicalities. One should prove the right representability theorems to be able to pass directly from the idea to a proof. Anyway, the refereeing process does not always improve papers. And in the case of this particular manuscript, the published version is, at least in my opinion, not as good as, I mean, somehow the beautiful idea at the center of it gets buried in technicalities. So I recommend the earlier versions of the treaty, of the paper, which you can see on the archive, or the appendix to my paper, which also has the central simple idea and very little else. Anyway, so this is so much for this. Now let's return to the first theorem of the talk. So the first theorem of the talk, many slides ago, told you that if you have a triangulated category with a good metric, then you can complete and you can look at the subcategory of the completion and you can define distinguished triangles in the subcategory. And with this definition, SFS is triangulated. And now, the second theorem, then I gave you examples. But the examples are really special cases of a very general example, which says that if T is a weakly approximable triangulated category, then first of all, T has a preferred equivalence class of norms. There's a preferred equivalence class of T structures. And each of them gives a metric, and a metric on T restricts to a metric on TC and on TBC. So you have good metrics on T, and therefore on TC and TBC. And for these metrics, you have that S of TC is equal to TBC, and under some condition, you can also go back. And the coherence is a technical condition I don't want to get into, but if R is a coherent ring, then you can go back and forth between the bounded complexes of finitely generated projectives and the bounded complexes of all finitely generated R modules. And if X is an Ethereum scheme, you can go back and forth between the perfect complexes and the bounded complexes of coherent sheaves. I mean, very early on in the talk, I told you that this was surprising. These were viewed as very different. The experts used to argue about which one was better. Now, this is not special to algebraic geometry. It also applies to the homotopy category of spectra. It turns out to be an approximable triangulated category and coherent. And you can compute all of the subcategories, and in particular, you can compute TC. It's the category of finite spectra. And you can compute TBC, which is the category of spectra that are built up of finitely many Eilenberg-MacLane spaces of finitely generated abelian groups. And the general theory applies, and it tells us that the S construction flips them. It passes between the finite spectra and this strange category and back. And now you can ask about all the others. So I've told you from this old theorem that you can pass back and forth between TC and TBC. And you can wonder, what about all the others? So recent work with Canonacco and Stellari says that you can always go down. So there's a recipe which takes any of the subcategories in the tower and in purely triangulated terms describes all of its subcategories. Now, if either TC or TBC has a unique enhancement, you can also go back up. So this tells you that, in fact, as long as X is an Ethereum scheme and Z is an Ethereum scheme, I have to say, and Z is a closed subset, then any of the 7 categories defines all the others. And the same is true for the homotopy categories. If I give you any of them, there's a recipe for passing to all the others. And so some of this is work in progress, but yes, let me not go into it. There's one paper that's already written, and the second part will hopefully be written sometime this year or early next year. And finally, for the last result that I want to mention, so suppose X is a finite dimensional Ethereum scheme and Z is a closed subset, then the category of perfect complexes is a bounded T structure. So maybe I should be careful. So these are the perfect complexes of on X whose restriction to X minus Z is acyclic. So this is a bounded T structure if and only if Z is contained in the regular locus of X. So it appeared as a conjecture in this article of Antio, Gepner, and Heller, and the proof may be found in this paper. And finally, I should say something about the idea of the proof. So if you have a bounded T structure, then you can look at the T structure in the unbounded derived category of quasi-coherent sheaves that it generates. And the key is to prove that this is in the preferred equivalence class, and then the general theory applies. And, well, okay, let me skip the rest of the details. And I've given you a long talk about 7 articles that I've written, and other people have written more about it. So there are 7 articles, most of which are still in preprint form. So Article 1 appeared in 2021. And in 2022, I gave a talk in Sydney in which I mentioned that, well, I will probably die of old age before all of these articles appear in print. But as I was giving this talk at Sydney University, and Brechje Pauws was in the audience, and she was a young postdoc looking for jobs, I mentioned that, well, through no fault of her own, her article was not even submitted for publication. If she applies for a job at the university near you, then please bear it in mind. And anyway, Geordie Williamson strongly objected. He told us that we should submit the paper, that papers get published out of sequence. And indeed, we did submit the paper, and the paper was published. And then paper 6 in the series was written to be logically largely independent of the ones earlier in the sequence. And so it was also submitted for publication and was accepted. And when the backlog of the journal allows, it will also appear. And as for the other papers, who knows, I might still die of old age before they all appear. Papers take a long time to appear. And when you have a sequence of papers that build on each other, this compounds the problem. But this doesn't stop other people from having written about it. So there are papers published by others, and there's more preprints by others. And thank you very much. I should stop now.
Thank you, Amnon. Really nice talk. Are there questions from the audience? Let's see if we have anything in the chat. No. Okay, so you can stop sharing, but unless
Okay.
you do.
Yeah, okay. Now I have to find out how to stop sharing. Oh, stop sharing. Yes.
Yeah, okay. Yeah, so I have a trauma with with all these talks that involve triangulated categories. The first thing the speaker always says is that it has coproducts. Mine doesn't. So,
Well, yes.
yeah, so, but I wonder if this completion process, whether this added, I mean, whether it becomes...
Yeah, it only needs countable coproducts. So it's probably, okay, I haven't tried, but it probably applies to the KK category. So
Yeah,
yes,
well, the C star category does have countable coproducts, but the algebraic one does.
Yes. So I think countable coproducts are probably enough for most of the theory.
But what I was wondering is whether when you complete, whether, I mean, that doesn't completion give you automatically give you the coproducts, or or you need to have them to begin with?
Well, no, the completion is no, the completion. Yeah.
Because you add colimits, don't you? Or you add colimits of
So, okay, so the completion as I define it all happens in the category of modules of your triangulated category. So it doesn't need to have co-products. So it happens inside an abelian category. So it's a strange situation in which you have a triangulated category fully faithfully embedded in an abelian category, and some other category, some other subcategory of the abelian category also has a triangulated structure, and they're related. And as it happens, the intersection, which can be zero, by the way, is a triangulated subcategory with respect to either triangulated structure. So it's somehow, okay, I don't understand it, but this, yeah, so there's some strange phenomenon happening there.
Okay, so yeah, you had lots of results, I guess. Yeah. Well, so and I share the feeling that of this problem that with the top journals usually mistreat authors very badly. I've suffered this some years ago. Yeah. Anyway, I have so there is a question from the audience. Would Radi Biswas wants to ask something?
Yeah, just a sanity check. Hi, Amnon. I think you spent 2 seconds on the coherent definition. I was just wondering if the definition had changed.
Sorry, I'm having trouble hearing.
He says if the definition of coherence has changed.
Sorry?
Whether this.
Hi, can you hear me now?
Yes.
Yeah.
I was saying you spent very little time on the coherent definition. I was just wondering if it had changed since I last saw it.
Well, yeah, it used to be called Ethereum. But
okay,
then,
so that's it. Yeah.
Yes.
Okay, thank you.
Yes. Yeah. As a result of Greg Stevenson objecting vehemently, I changed the name to Coherent. So, consistently. So.
Hi, thank you for the talk. It was very, very interesting. I have also a question. I mean, in triangulated categories, there is also this other metric that has been highly popular, that it's related to the stability manifold. And
yes. Yes.
Is there some kind of relationship between these two? I mean, or
no? The stability metric is Archimedean. It's not non-Archimedean.
Right.
And its translation it's invariant under the shift. So no, so on the
right, yeah, and one compactness doesn't imply the other.
Yeah, no, I have no idea what the completion with respect to that. Okay, I should say something. So the way I defined completion is breaks with the literature. So I defined completion, the completion of a category with respect to the metric was defined in the, you look at the Yoneda embedding and look at all colimits. And the problem with this definition, so this is simplistic, and already the old guys knew that for arbitrary metrics, it doesn't work. So the problem is that with this definition of completion, the category is not usually complete. With the completion has a metric, but it's not complete with respect to the metric.
Right.
So the way Kelly deals with it in his 1982 book is to iterate the process, and if you do it often enough, then eventually you end up with something that's complete with respect to the metric. So I'm cheating. The metrics that I study are sufficiently simple so that the simple-minded completion is complete, and there's no need to go any further. But the reason I got into this is because the stability metric doesn't satisfy this.
Mm-hmm.
So it's
the completion of this. I mean, it's it's extremely difficult to. This metric, it seems to be.
So you probably need to do the sophisticated thing that Kelly does, and I don't. I have to confess, I haven't thought about it. I don't know what you get.
Yeah, no, I mean, okay. Paolo might not do much more than me, but I mean, there has been all this technology on reducing things and trying to find smaller triangulated categories that would sort of live in the border of your manifold and so on, but it goes completely in a perpendicular. There are two very different. And I wanted to know if there was some kind of relationship that I was missing. Yeah.
It would be interesting if there's a theory that covers them all.
Yeah. Cheers.
Thanks.
Do we have any more questions? Okay. Otherwise, we'll stop the recording now.